Day of the workshop, and today's focus is on knotted or topological flux tubes in cosmology. And to start out, we have Achucarro from Leiden University.
Lost my presentation. It was supposed to be in mirror mode. We like this.
Sorry, do you call someone? Do you need some?
No, I think it's fine. So thank you very much for the invitation and better? Can you hear me? You can't hear me.
Hi, Mary.
Can you hear me?
Yeah.
Yes. So the organizers asked me to give a sort of quick review of cosmic strings. As you see, there are several talks on cosmic strings following, and so I'm just trying to set the scene. So basically, so that you know where the various talks fit. I'm not completely sure of what the contents of the other talks will be, so this is my best guess. Don't take it personally if I misquote you, please. But the one thing that I did want to throw in at the end, given that you're an audience who's interested in magnetic fields and knots and things like that, there's some exotic things that we have found working with the simplest cosmic string there is, which is the abelian Higgs string. And I thought I would just show them to you in case you find them interesting. So the talk will have a part which is introductory if you want, and then I will show you some things that you probably have not seen before. And my apologies to all the cosmic string experts in the audience who did most of the work on the slides, even if they're not mentioned. So, let's see. So it's going to be 40 years of cosmic strings, and they've gone through ups and downs, and but 10 years ago, there was the incredible discovery that perhaps it's not just regular flux tubes that could be out there, but also superstrings. And that gave an impetus to the whole field, but also it sort of changed it slightly in terms of emphasis, because the two types of networks are different. And so the way one looks for them in the cosmos is also different. There have been interesting changes of perspective after cosmic superstrings. And you would see, for instance, more complicated networks. Well, I mean, this had been studied by the cosmologists before, but things like you can have beads, and perhaps the bead is something that it's a string that is wrapping in some extra dimension, and it looks like it's a bead to you in 4 dimensions. You will find interactions between strings which have gauge fields and global symmetries, and that gives interesting behavior, and so on. And the other thing is that the main detection for cosmic superstrings is by gravitational waves, which is not the case for the regular cosmic string. So that again has launched searches in that direction. So I note, as many years in this field, that we've gone from putting bounds. I mean, we're still putting bounds because there's absolutely no evidence of cosmic strings. But now every major project, whether it's Planck or whether it's LIGO, whether it's whatever it is that they're doing astronomically, includes a science case for searching for cosmic strings. And I think that's it's a reflection of the fact that it's such an interesting thing. If we could find it, it would really give us a window on physics at energy scales that we have no hope of understanding. There is some problem, which is that some of the properties, some of the signatures of cosmic strings are very well understood. They depend on the long-range behavior of the network, so large scales. There are other properties, like the gravitational radiation and in general decay products, that are much more dependent on the small-scale structure on the strings. And there's a slight problem in that that's not fully understood yet. And so some of the talks and some of the discussions are still trying to understand what strings do at very short distances, because that's what controls, for instance, the radiation they emit. And so there's still some unresolved issues, as I say there. Now, this is the initial paper by Kibble in '76. And I think the idea is completely known to everyone here. Anybody who knows vortices in super fluids or in a superconductor is familiar with the idea that you can have a line where the energy concentrates. And so from the point of view of particle physics, you are looking at, you have a ground state, which in the superconductor would be, for instance, the Cooper pair wave function. And you would be looking for, oops, sorry. There. You have the possibility to have a vacuum that points in many directions. If you have a whole circle of those, then as you come in, you reach a point where the vacuum has to go away, the field has to go away from the vacuum. And that's the point where the energy is concentrated. And it typically is concentrated in a core of about the inverse mass of the field in question, in units that, of course, I should say the Compton wavelength of the field in question. So here's a typical way that we would do it with a Mexican high potential. You know, it's when the field is zero, there's potential energy, and so that potential energy concentrates here. And if I now imagine this would be one plane, but if I move the plane away from the board, I end up with an entire line of zeros by continuity. I cannot remove it. And that's the role of homotopy in determining the strength. The abelian-Higgs model is the relativistic version of the Landau-Ginzburg superconductor. And so, again, it should be familiar to all condensed matter physicists. The only thing I would say, yeah, whoops, okay. So you know that in superconductors, I have to distinguish between type 1 and type 2. There are two fields. One field is the scalar field, which would be the wave function of the Cooper pair. And then there is the electromagnetic field, which is this A mu there. And I can form vortices. The vortices have a quantized amount of magnetic flux. Okay, and the only thing I was saying is that the ratio between, so these numbers are not so important. I should think about it in terms of the mass of the two fields involved. And when this ratio is less than 1, this is when the mass of the scalar is less than the mass of the gauge field, then I am in a type 1 situation. I say it later. And otherwise I'm in type 2, and they have different properties which will be relevant later. So here they are. This beta parameter that I was saying is important to the dynamics, and it's the ratio of the masses. So type 1, for later, please remember that if I have two parallel vortices in type 1, they will attract. And if I have type 2, they will repel. And there's a supersymmetric, very important limit in between. I won't be saying anything about this today, but it goes under the name BPS, which you probably have heard when you hear string theorists talk about defects and branes. And so for that limit, there's actually no interaction between the vortices. So, okay, let me just quickly review the idea in Kibble's paper. You're in the very hot universe, you go through a phase transition, and your vacuum changes. Your vacuum changes from being the potential energy, which is minimized here, and then as you lower the temperature, at some point you begin to realize that this was a Mexican hat that you hadn't quite noticed. And so when you're in the hot temperature phase, you're fluctuating, so the direction of these arrows could be anywhere. As I go down through the phase transition, these become the vortices that we had before. Okay. And so you can see that the amount of strings that you would expect in 3 dimensions is you're going to get approximately, if you look at the size of these domains, which is given by causality, it has to be, at most is whatever light could travel, but in a realistic phase transition, it's actually usually much smaller than that. So you would have domains of a particular size where the field is correlated, but then there's no correlation between them, and so you expect to form, if you get one of these strings, you would expect to form approximately one length of string per volume of one of these domains. So it goes like 1 over the length, the correlation length squared. And this was Kibble's essential insight, is that if strings are possible, they will form simply because the universe is so large that there's many, many, many of these domains. And it's simply a question of causality. I mean, light cannot propagate fast enough to equilibrate all those domains. So in superfluid helium, you would do something like this. You would create a small phase transition by perhaps bombarding with a neutron. And, and then you get and then you get again these domains where the field is pointing in various directions. When 3 domains meet, you have a chance of forming a string, and you end up with a tangle of strings. Now, initially, the scale invariant distribution of loops, I said that many of these things were done by people in this room, and Tanmay is sitting there. So initially, you expect some sort of scale invariant distribution of loops and a random walk for the network of strings. And then the network starts to evolve, and the strings start to stretch, and the correlation length grows. So the strings become straighter, and they start reconnecting, forming loops, and throwing energy into radiation of various forms. And so the important thing is that the result of all that seems to be a self-similar solution, which is an attractor, and it's called the scaling solution. And from the cosmology point of view, what is essential about this solution is that it doesn't come to dominate the energy density of a universe. So we know from for instance, nuclear synthesis, or from the elements, that we can map the expansion of the universe quite well, and we know the universe had to be radiation dominated. So the evolution of the universe had to be dominated by a content in radiation. And so it's important that the strings don't spoil that. And they don't spoil basically the standard cosmology that we know works so well. And you can see that in the scaling solution, the strings are actually scaling in the same way as the radiation, so 1 over time squared. And if I'm dominated by radiation, well, perhaps it's 400 times this parameter. I'll say this in a moment, but it's, in the most optimistic cases, perhaps it would be something like 10 to the minus 6. So you're looking at a very small component of the standard cosmology, which is sitting there, and it's basically stays constant as a function of time, and you can go through with your standard cosmology, but with this string component there, and perhaps there's the possibility that this component is detectable. And I was saying that here the G mu is the mass per unit length of the string, and G is Newton's constant, and so this with a bunch of H bars and C's that I didn't write down is actually an a-dimensional dimensionless number, a-dimensional. And so it's a measure of the mass per unit length of the string. Okay. Now let me, I said I was going to throw some exotic things, which you might find interesting. So let me just throw one for the record. The homotopy, so forming these networks of strings, it's very, I'm saying that the homotopy of the vacuum manifold is important because I have to force the presence of those zeros. But this actually, it's not absolutely essential. You could have networks where the strings are not topologically stable. And so the example is semilocal strings. And semilocal strings is simply a multi-component superconductor where I have more than one scalar field, but only one type of electromagnetic field. And so the electromagnetic field forces certain alignments between the scalar fields. And so, So this would be the type 2 situation. In the type 2 situation, they're completely unstable. They don't form the strings. But in the type 1, they're actually stable, and they form at fixed radius. And this was certainly work by Tanmay and by Mark, who's sitting there. And you have a reference there. But let me just show you how this happens. I'm going to sort of go through the transition. There's no expansion here, but I'm not sure how to activate this. Does this work? So I'm going through the transition, and I'm creating flux tubes. Those are magnetic field flux tubes, but as you can see, they're open. The strings have ends in various places. And these flux tubes, some of them are shrinking, and some of them are growing to try to meet with another end of another string somewhere else. And somehow the end result of this process is that you end up with a network which looks a little bit like as if the strings had been topological. Okay, so there you go. You saw here something running, whereas this loop is shrinking, and so on and so forth. And so this is one sort of exotic type of superconductor, if you want. I saw that there were talks about multi-component superconductors later in the week. Unfortunately, I don't know whether anything like this is relevant to them, but I thought. In any case, this is in a box which is not expanding with the universe. If you put it in a box that is expanding with the universe, then you have some competition between the ends trying to meet and the universe expanding and not quite letting them, and so it's still an open question what the end result, or what the scaling attractor, if there is one, is in that situation. It's one of those things that we still don't know, but in any case I think Carlos will discuss some of this in your talk. Okay, so as I was saying, scaling is absolutely fundamental for the evolution and for the cosmology, for the health in the cosmological evolution of these networks. And it's simply the fact that the correlation length is expanding, it's growing, but relative to the correlation length, the network is self-similar. So, and this is maintained thanks to a process known as interconnection. If I throw two vortices, what am I going to tell you about interconnection? You throw two vortices together, they exchange neighbors, and they go about having exchanged. And so you have it here. And the reconnection is very important because it's what allows the strings to maintain small-scale structures. So every time I reconnect, if a string reconnects itself, it can form a loop. It's further down. It can form a loop, and so that loop is then free to decay by radiation, and at the same time it forms kinks in small-scale structure, and those kinks themselves will also radiate. So if you didn't have reconnections, then the network would completely dominate very quickly. Okay, so I think by now I have said most of this, or rather all of it. So scaling is possible because the strings lose energy very efficiently. And again, here is another thing that is not completely understood. It's clear that if I put strings in the universe, then for sure they can radiate through gravitational waves, and that's a very efficient way of losing energy. But strangely enough, if I use in simulations where there is no gravity anywhere, the strings are still managing to scale somehow. And over there, the only thing is that they're emitting radiation and particles directly. There's no gravitational radiation. So again, this is something that Mark has been working very hard to understand. And the evidence is that scaling is there no matter what. So I mean, the tendency to scale is very strong. This is what I was looking before. So if I reconnect, a string can form a loop, or two loops, or in fact, if in simulations, what you see very often is that you have very large loop, which is very non-planar, very complicated, and then it self-intersects and it forms maybe 20 at a time. So it's a very efficient process to create a smaller structure. Okay, so the scaling solution for a billion Higgs is something like order 10 to 40 long strings in our observable universe today, plus a population of large loops, which would be about 1/10 of the size of the universe, the horizon, and then a population of smaller loops, which where there's some discussion as to exactly when they start scaling, and it seems like these ones may take more time to scale. So you have a long transit with those. Okay. And this is a direct decay that appears in Mark's and everybody else's simulations where you don't have gravitational radiation. Okay, so could the strings be detected? They're just a small fraction, so perhaps, if we're lucky, we could see them. And basically, the detection strategies are, you could say, 2, maybe 3. So there's one important thing, is that strings have a very peculiar gravitational field around them, and so this leads to very distinct signatures. If you were to see one of those, then you would know it had to be a string. There's nothing else that can reproduce it. And so those gravitational effects, which I will talk about in a moment, give rise to, in particular, if you illuminate from behind with the cosmic microwave radiation, they lens, they give anisotropies, they do all sorts of things. and they also create wakes. I'll talk about this a bit more. And then the other possibility is that you simply look for the decay products, whether they are radiation or and there you gravitational waves is one, cosmic rays is particles, so that's also a very important possible source of decay products. And then depending on the type of string, you might also get electromagnetic bursts of some kind, but for that the strings have to be of a particular kind. So the abelian Higgs wouldn't be able to do it. Okay, the important thing is that the predictions on all of these things depend, of course, on the mass per unit length, because that's the one that determines the entire scale of all these effects. And they also depend on the network density. So if I have a very dense network, I'm going to see much more radiation, so all the stochastic backgrounds go up. But they're also subject to these theoretical uncertainties, which are being, there's a lot of progress in that direction, but it's still not completely finished. And then the other thing that you might have is that I think Richard Batty is going to talk about this, and I think Misha Volkov also, is the possibility to have stable loops of string. So if the string, in particular cases when the string is not just abelian Higgs, but it carries some extra current, it's let's say superconducting, superfluid, something like that, if it has some mass current in it, then that mass current can stop the collapse of a loop and give you a remnant which doesn't go away. And the problem with these remnants is that they disrupt. I mean, if they're too heavy or if you have too many, they can disrupt nucleosynthesis or they can overclose the universe. So you have to be very careful that they do not spoil cosmology again. But I think here probably what Richard is going to be more concerned, and probably Misha also, with whether these things really are stable, whether you can find them, whether they're there, and so on. Okay, so one of the most important set of constraints on certainly the mass per unit length of the strings comes from the cosmic microwave background, and I'll leave that to Paul, who's speaking after me. I think he's going to explain. There's a lot of things that the strings can do in the CMB, and but in particular, perhaps the most important is that they do not produce. So this is the Doppler peaks that are seen in the cosmic microwave background, and the strings don't produce those peaks. They produce a sort of bump, and so you know that they cannot possibly be the dominant source of the anisotropies. And since we think that those anisotropies reflect the initial density perturbations of the universe from which everything appeared, then it's clear that the strings cannot be the source of those primordial density fluctuations. So at most you may have this superimposed on this other pattern, maybe at 5% in power, something like that. And the numbers, of course, keep going down as the CMB gets better. I'm looking at Paul. Planck is out there measuring, so you're going to tell us something. Are you going to tell us? He's not going to tell us anything. Okay. Well, in any case, so the bounds come. This parameter, this mass per unit length in dimensionless units, it's always of the order of less than a few times 10 to the minus 7. And depending on who you ask, the number in front may change a little bit, but this seems to be the bounds from cosmic microwave background. Well, so if you look at this, you would say, okay, well, end of story. So for many years there was this competition thinking which of the two mechanisms would generate the primordial perturbations. Was it inflation or was it cosmic strings? And of course, the moment these peaks were found, that was it for cosmic strings. They were not the main source of anisotropy. They might still be there. And so for a while, mentioning cosmic strings was like mentioning the devil. What are you doing working in cosmic strings? You can't possibly, it's not, they're not there. And until it was realized that in fact many very well motivated models of inflation end producing cosmic strings. So you have your inflation, and then at the end of inflation you find yourself with a tangle of strings sitting there on top of the perturbations from inflation. And so this is a typical example where you would have a potential that looks like this. These potentials are called hybrid inflation. potentials, and so you would come down here while the universe has a very large, moving very slowly, a very large potential energy and not very much kinetic, so it's slow rolling here, and it's producing all the density perturbations that lead to the Doppler peaks, and then at some point the field these are called the waterfall fields, so the field falls one way or the other, and that's the end of inflation. But the interesting thing is that if you're doing supersymmetry, your fields tend to be complex fields, and so these two things here are actually part of a whole circle of vacua that I could have ended up in, and so that's where I get the strings. It was also realized around 2003, I said about 10 years ago, that in fact even superstring theory seems to have their own cosmic superstrings, and they would form at the end of inflation, when inflation is generated by brains. And so, a brain is some surface on which the fundamental superstrings can end. And so here you have a sort of here. You have a depiction of this brain with strings attached to it, and the strings are moving, and there's little loops going back and forth, and so as long as if you have two brains, it's possible to create a period of inflation. And then at some point, the evolution becomes too fast and inflation dies. And so you get this thing, which is the annihilation of the brains. And at that moment, you re-enter the Big Bang cosmology as we would know it. So this is the hot, expanding universe that cosmologists like to talk about. And the expansion eventually leaves us with a universe with some cosmic superstrings, and some of them are in our 4 dimensions, and some of them are sort of wrapped around some of the other dimensions. Because, of course, all of this is happening in 10 dimensions, because there's a superstring now, superstring theory. And so all of these 4-dimensional brains that we live on have also a compactified space. The other 6 dimensions have to be there somewhere. And maybe they look like this, or maybe they're bigger, or whatever, but the point is there's more dimensions than what we see. And and so here, here's my depiction of a brain, which is not very good. Now, cosmic superstrings, if I do form a network of cosmic superstrings, it's actually different. It has some important differences with respect to regular cosmic strings, so the usual abelian Higgs flux tubes that I was talking about. And basically the differences are, the number one is, the most important difference is that they naturally have a much lower mass per unit length than the flux tubes would have. And this is simply because in order to be able to produce inflation, you need to have everything redshifted or gravitationally redshifted. And so that means that in particular the masses of the string you also see much lower than you might see them if you were close by. And the reconnection probability is the other thing. These things, for 2 reasons. One is that when you think they're crossing, perhaps in the higher dimensions they're not even crossing, so there's no reason why they should reconnect. And the other reason is that even if they do cross, these things are quantum objects, so there's some probability of reconnection, but it's certainly not 1. And so you can get reconnection probabilities somewhere between 1,000 and a tenth. So for every 10 events, maybe you get 1 reconnection maximum. 10 events. Okay. The other fundamental difference between cosmic superstrings and the regular vortices that one is used to is that these you get these sort of multi-tension networks with junctions, and that's because here's a fundamental string, and this is a one-dimensional D brane that you call a D string, and so the fundamental can end here, and the flux sort of dissolves in it, and then the D continues here, and it goes there. And so you have to, the fundamental strings are carrying p units of their own flux, and these D strings are carrying maybe q units of their own flux, and so over here you have to have both p and q, so the fluxes are conserved, and so you call these things pq strings, just to indicate that you have 2 different kinds, and they each carry and conserve their own flux. And there will be several talks about this, so I don't think I have to say much more. But I did want to spend a little time on the gravitational effects, and Tanmay has signaled 10 minutes. So then perhaps I have to make a choice between showing you some gravitational effects or showing you some curious intercommutation issues with abelian Higgs. So I think what I will do, let me just do the gravitational part sketchy. I'll just show you some images, and then I'll show you the intercommutations, because I think you may be more interested in that. The gravitational effects really would be a smoking gun, because the space-time around the string, if I take a straight infinite string, it basically eats up a cone in your a wedge in your space-time. And well, never mind. It's something like this. If I have a string here into the blackboard, then the space-time around it is as if you basically remove a wedge, and so it becomes like a cone. And so you can see that if you have for instance, two light rays coming towards you, they are parallel, so they're emitted far away, and in fact to you they will converge. So there's things like lensing of light. And the lensing happens in such a way that it's very distinguishable from other sources of lensing. But and it's simply because of this wedge that you have removed. Now, if the string is moving, then the wedge, you can imagine the wedge going sort of behind the string. It's just a way to think about it. And then anything that is behind the string gets pushed towards you, and so everything gets blue shifted behind the string, and so you get a very discontinuity in the temperature of any light or anything that you see from behind. And the important thing is that you would get here, for instance, for the lensing, you would get identical images with absolutely no distortion. So I was going to explain this, but let me not do it, and instead let me just show you what a string would look like in the sky. So suppose there were a cosmic string there. This is just an image from Hubble, and you put in the string in there, and so what you would see is this. Okay, the cone sort of opens. You see two images for anything that is behind the string, and as you can see, the images are completely identical, so there's no distortion. If you see something like this, then that's a smoking gun for a string. There's nothing else that it could be. And there was a few years ago, there was some tantalizing candidates which lasted for a long time, and the two spectra from the two images were absolutely identical, or it seemed identical, and it really took a Hubble image to prove that it wasn't, that it was really two galaxies. So we all got very disappointed, but okay. And now, this is from Hubble Space Telescope. They're also looking for these sets of images aligned, and so far they haven't found anything. But it's like a needle in a haystack, literally. This is all different kinds of lensing that I would have talked about, but let me just move. And again, everything that we know is that the mass per unit length is something like a wedge of 10 to the minus 7, a fraction of 10 to the minus 7. Let me just pass this since I've already said it. So for radiation, here is just one quick image of a cusp. The strings, if you have a loop and it's oscillating, then on average once per oscillation it may create a cusp like this. And so this black is what an infinitely thin string would be doing if you just solve the equations for a string moving on its own tension. And this is what is actually happening for real in the field theory. And you see that they emit radiation very, very in bursts, and very directed bursts. And so, this is one of the things that you are looking for. Again, if you see a burst, depending on what it is, it could be due to a cosmic string. Okay, no time to talk about this, but fortunately other people will. And I was just mentioning the various ways in which you can try to analyze this network, and you can try to do numerical simulations, but the numerical simulations have to resolve an incredibly wide range of scales, and so there's many tricks to do it. And then at the same time you have sort of analytic approaches with which you try to patch the various regimes that you're simulating. So, okay, so this is just how am I doing? Okay. I'll just show you. I'm back to cosmic strings of the regular abelian Higgs superconducting vortex, whatever you want to call it. And I'm looking at the process of intercommutation. The reason why I'm interested in intercommutation, as I said before, is because intercommutation is fundamental for the way the network looks and scales. Notice that every intercommutation produces 1, 2, 3, 4 kinks, and these would then move at the speed of light up the string. Okay. These are the small scales. These are the generators of small scale structure, which then allows for radiation, for decay into radiation and so on. Now, I've said this, so let me just pass. Let me just take abelian Higgs, completely vanilla, nothing special about it, and I just want to mention that you can really push the type 2 into very deep type 2 and type 1 into very deep type 1. And then this thing that I mentioned, that parallel vortices attract and parallel vortices in type 2 repel and in type 1 attract, all of a sudden begin to play a role in how the strings intercommute. Now, the expectation is that if I throw any abelian Higgs for any range of parameters, doesn't matter, the strings will reconnect. And it was observed by Paul already many years ago, 20 something, that if you throw them very fast, then that may fail and the strings may pass through each other. So let me show you why. If you throw two strings at near the speed of light, they reconnect. Oops, sorry. They do reconnect, but the reconnection creates these 4 kinks that I was talking about. And the thing is, if the string is moving very fast in the transverse direction, then these kinks are already moving almost at the speed of light in the transverse direction, so they get very small velocity up the string. And so you form a bridge. There's no distortion of the intermediate portion that you create. And so if you look at how the arrows are pointing, this one is going that way, this one is going this way, so in fact you've created a vortex-anti-vortex pair in the center, and it's sitting there, almost static, so at some point the two see each other, they reconnect, and then the strings pass through. Okay? And this is how the reconnections would happen most of the time, if you're in, say, type 1. And I can show you, let me show you some example. This is a type 1 reconnection. The interesting thing is that if I go into the deep type 2 regime, then something completely different happens. And instead of, so when I reconnect, when I reconnect, there's a loop that comes. So the strings do reconnect, and then in the region between them, a loop comes rushing up and catches. Catches with the string. Okay, produces another reconnection, and then you get a string looking like this. So you really get 8 kinks in this case. And I, for one, don't know why in type 2, in very deep type 2, you get something like this. And in deep type 1, it's such a clean double reconnection that I can explain with a bridge. And moreover, I have to go really deep in type 2, because if I look at ranges between, ratios of masses between 2 and a little bit more than 2, then I get something that looks like it's a loop, but then if I see what happens next, the loop is absorbed. So it was never a loop. It's actually, a bridge with some energy, which is sitting there. And this is, again, surprising. We don't know what's special about going between, let's say, between twice a range of masses between the scalar and the gauge field of a factor of 2 or a factor of 4. Something completely different happens. So we started. I'm just going to finish with one image and one film. We started looking systematically at this process, and then we realized that, in fact, you can get even multiple intercommutations. You can get triple and quadruple intercommutations when you are very deep and very fast. And so let me just show you how this happens. They happen. All these double, multiple, so 3 reconnections and 4 reconnections happen on the boundary between where you would expect regular reconnecting once and reconnecting twice. And here's my last image, and I stop because I see I'm over time. This is how a triple reconnection would happen. Well, yeah. So it's slowed down tremendously. First you reconnect. Now you will see the loop. The loop catches up. You get we're back to where we were before. But now there's so much curvature in the central part that the strings get pushed against each other. And then they reconnect a third time. And this could happen 3 times, 4 times. I mean, we've seen up to four reconnections. We don't know if much more than that is feasible, but at least this we understand. But what we don't understand is why there's a loop in one case and not in the other. So I think I'll stop here because otherwise I'm over time and we have a long session. Sorry.
One question. To what extent should we think of the reconnection process as analogous to a vortex reconnection process? In the sense of, understanding reconnections even in classical vortex or a quantized vortex is very, very involved. And you can do numerics and you can get to some extent towards the answer. But it's not clear that they completely capture everything.
I mean, this is vortex reconnection done numerically. This is precisely what it is.
Precisely what it is.
It's exactly.
In een Higgs-model zat er een superpolarity discrimination. What it meant kind of system. It's the same equations.
Okay.
It's not special.
One last question. Anyone?
This looks sort of chaotic. The next sort of resonant
yes,
process.
yes.
It's like kink collisions that sort of oscillate.
Yeah.
That's what I was wondering.
Definitely. It's you could say it's fractal somehow. I mean, you never know if it's going to happen.
Okay, let's thank Anna again. It's been a little short.